such a great opportunity for Riverlane to be here with you all today. Since this is our first year attending and sponsoring Q2B here in Tokyo, I wanted to spend just a few minutes introducing you to Riverlane, who we are, what we do, and what we're looking to accomplish collaborating with some of you here in Japan. So our mission at Riverlane is to make quantum computing useful sooner. And one of the ways that we definitely do this is through our partnerships and collaborations. We see this as being a collaborative thing throughout the ecosystem. Our company in particular was founded by Dr. Steve Brearley, who's here and speaking later this afternoon, in Cambridge in the UK back in 2016. It's currently 90 team members, primarily made up of engineers, scientists, and physicists, working on quantum engineering problems and solutions. So very aligned with some of the presentations we've seen already this morning about how to solve the fundamental problems with quantum error correction and quantum hardware that will get us to a point where we can solve useful applications within the industry. So today, we primarily work with the UK and US government. We have hardware collaborations globally with other hardware labs, startups, academic institutions. And then we also work with enterprise companies because we want to fundamentally understand the industrial use cases that these enterprises are looking to invest in and solve over the long term. So as I mentioned, we are a global company. We currently are headquartered in Cambridge, UK, where we were founded. But we also have offices in Boston, in the United States, as well as San Francisco, where I'm based, and are looking to expand because we see quantum computing, we see a supply chain developing. We see it as being a global supply chain. And at Riverlane, anyway, we strongly believe in making very strategic local investments in the resources that we hire and the partnerships that we create. We want those partnerships and the investment in the talent to be working locally to collaborate and to really invent the next generation of technology for this ecosystem together. All right, great. So let me spend a little bit more time then on our specific journey to quantum value at Riverlane. There's a couple of challenges that I wanted to highlight, at least as part of this talk today. And again, that's getting to quantum scale, right? Getting to thousands of available qubits. And at Riverlane, so we're not actually creating qubits ourselves. So we do a lot of this work through collaborations with other hardware companies and academic labs and institutions. And then the second challenge that we see at Riverlane, that's really our primary focus, as Sebastian alluded to in the last presentation, is making every qubit count, making those qubits useful. And so the reason that making qubits useful is so important is because inherently these qubits are fragile, they're susceptible to noise, and this causes decoherence. Over time, this makes them less valuable for doing any sort of real computation or computing. So when we talk about quantum error correction, what we're really talking about is how we create logical qubits from many different noisy qubits. And what we believe, and I think this has also been mentioned in several of the presentations, is that there's some significant breakthrough in the number of qubits that are going to be required. Sebastian's presentation from Universal Quantum had some numbers. I've seen several numbers. You know, what we're talking about at Riverlane is this is a massive improvement on the order of like 10,000 times the reduction of system errors that we're ultimately looking for. And so this will be a combination of the improvement in the fidelity and number of qubits from the hardware partners in the ecosystem. This will be improvements in the classical computing techniques that we use to control those qubits. And this will also be improvements in things like decoders and the ways that we implement those decoders. So at Riverlane, the software side of the solution we call deltaflow.os. This is our version of the operating system. It includes things like system tools, the runtime, the underlying control system software that integrates with the control hardware and the decoders. And ultimately, we see that as kind of the middleware layer where the eventual applications will run, these industry applications that are going to be amazing for things like materials science, pharmaceuticals, new drug discovery, clean energy, those types of breakthroughs that we're all here for and interested in investing in quantum computing to ultimately solve. And so for us, What that OS really looks like is it's the actual error correction cycle, where we're observing the qubits. We want to obtain the syndromes, determine what errors have occurred, and then schedule corrective actions based on detected errors. So for us, it's kind of a seamless process. We can do a lot of that offline today, where we're taking the information, doing what we call decoding over the weekend, fixing those errors, and then implementing it maybe in the next experiment or run. But ultimately, what we're trying to solve as an engineering company at Riverlane is how do we make a real computer out of that, where we're doing this all in real time. So in addition to providing one of the world's most highest performing software decoders today that we can implement, we're also providing this infrastructure, this decoder on an FPGA. And we've also very recently built the world's first decoder on an ASIC chip. And the reason we're going down this path is because, again, fundamentally, as the number of qubits scale, we're talking about a data processing problem that has never been solved or attempted, really, in the history of technology, in the history of engineering. And so we want to optimize the techniques that we have in our decoder, invent better, newer decoders today at the software layer. Ultimately, we need to bring that down to the hardware layer in the form of FPGAs to integrate with the existing systems. And then finally, when we really make that breakthrough in quantum computing, this is going to be chip-level integration. And so we see ourselves, again, as part of that supply chain I alluded to earlier. And we're constantly collaborating with hardware companies working on the qubits, manufacturers working on the chip technologies. These are the types of collaborations that we're interested in talking about and why we're here this week in Tokyo. Finally, we also provide a control solution as well. It's integrated into that OS that I described earlier for us. It's decentralized architecture, fully open. It integrates with multiple hardware ecosystems. We have control engineering support that can come on site, work with people in their lab to get it set up and integrated. And just to give you an example of what the interface looks like, so that's one of our calibration routines that can be dragged and dropped. It's a Python-based interface and fully customizable. So then just to wrap it up for us at Riverlane, I'm here along with Dr. Steve Brearley. If you're interested in these topics, especially related to quantum error correction, he's going to be giving a much longer, more in-depth talk on that subject later this afternoon, which I would highly encourage each of you to attend. And we've also got Dr. Rebecca Simmons here with us sitting in the back. So any of us would be happy to talk with you at the lunch break or any of the other breaks throughout the week, networking reception, or if you don't see us, feel free to email me. My email is there on the slides, which I'm sure will be shared. So that's great. Thank you all so much for your time today. Really appreciate it. Thank you.